In this video, we're going to talk about how to calculate probability and how to calculate the expected value and standard deviation using shortcut formulas. We'll go ahead and start with the expected value and standard deviation. So if x is a binomial random variable, so if we know that we're in a binomial setting, we can express x as a binomial distribution. And we would write it this way, x tilde b. And in parentheses, we put the details of the binomial distribution. And you'll notice there are two variables there, n and p. N is the number of trials, and p is the probability of success. So we need those two pieces of information to know what a binomial distribution looks like. To calculate the expected value, we simply take the number of trials and we multiply it by the probability of success. Pretty straightforward, n times p. For example, we talked about flipping a coin 3 times. If I do 3 flips, n is 3. Probability of getting a heads is 0.5. 3 times 0.5 is 1.5. And that's exactly what we saw when we did that calculation manually. The shortcut formula for the standard deviation is the square root of n times p times 1 minus p. Why 1 minus p? 1 minus p is equal to the probability of getting a failure. In this case, the probability of getting a tails. This is also sometimes in some books called Q. I oftentimes call it Q because the textbook I learned from called it Q. And that shortens it a little bit, square root of n times p times q. I do not, unfortunately, off the top of my head, remember which notation your books use, but both of those are valid. It's the number of trials times the probability of success times the probability of failure, take a square root. So for our flipping a coin 3 times, it would be 3 times 0.5 times 0.5, and then square root. To calculate the probability, we have a formula to do that, and it involves that combination formula that we learned earlier, or we can use a TI-84, and we'll look at both. If I want the probability that I get exactly 2 heads when I flip the coin 3 times, that's going to be px equals 2, sorry. So that's a single value for x, and we use NCA times p to the a times q to the n minus a. And you may be asking yourselves, why? And that's because, let's say I flip a coin 3 times, and I want 2 heads. So probability of success to the number of successes times probability of failure to the number of failures times all of the different ways that I can arrange those successes and failures. So that's why that combination is showing up. If I want to do a range of values, I just have to remember that I add up all of the individual probabilities all the way up, let me fix my notation here, to x equals a. And you can see how this could become messy very quickly and why we typically do these calculations on our calculator. And you will see I have a breakdown here for what that's going to look like, and there's an awful lot more. We have two groups. This is for a single value, x equals a number. That's always going to be a PDF, probability distribution function. These probability statements have inequalities in them. X is less than or equal to A, X is less than A, greater than A, greater than or equal to A. In those cases, we want a cumulative distribution function, because we want to add up the probability over a range of values. We want to do this, and we know adding up as we go means cumulative. So on our calculator, if I'm doing PDF, I'm going to go to, I just had a brain fart, sorry, second, and then I'm going to press the vars button. Second and vars. So let's go ahead and do that on our calculator. Second and then vars. And you'll notice it takes us to a distribution menu. And if you scroll down somewhere on here, option A says Binomial PDF. So A, Binomial PDF, in parentheses, and it's going to ask you for some information. For all of these, instead of Binomial PDF, I'm going to want Binomial CDF, which is option B. And they're going to ask you for some information. So let's pull up this data and see what it asks us for. So we'll go down to A. And I can see it's asking me for N, P, and X. N, P, and X. If I go second vars and I look at normal CDF, it asks me for the same thing, N, P, and X. So here, N, P, and I'm looking for X equals A. I'm going to put whatever that A number is, N, P, A. Now I run into some issues. My calculator is only able to do those types of calculations. So what happens when I have one of these inequalities? The answer is we do some modifications. If I want a less than, meaning I don't want to include A, I'm just going to start my Binomial CDF one number lower. N, P, A minus 1. If I want less than 2, the next nearest number is 1. I would start at 1. If I want greater than A, greater is the complement to less than or equal to. These two things complement each other and cover the whole number line, cover the whole sample space. And I know the complement trick, so this should just be 1 minus Binomial CDF of NPA. If I want greater than or equal to, meaning I want to include this number instead of excluding it, I need to drop this down by 1 because I want to be doing the complement to this guy. So 1 minus Binomial CDF of N, P, A minus 1. The trick for you is figuring out where you're at. On test day, you are allowed to use notes. It's an open note test. You can look this up in your notes. So what I would encourage you to practice is, as you're going through your homework, practice that connection between the English words for inequalities and the mathematical symbols they go with. I've included in your week 2 videos and resources a link to a document that transcribes English words into mathematical inequalities. So you might want to check that out. We're going to go ahead and do an example so you can get a feel for how this works. So for our example, it says, during a certain NBA season, a player for the Los Angeles Clippers had the highest field goal completion rate in the league. This player scored with 61.3% of his shots. Suppose you choose a random sample of 80 shots made by this player during the season. Let X equal the number of shots that scored points. What is the probability distribution for X? So if I go through this, I have 2 outcomes: made the shot, didn't make the shot. Each shot should be independent of his last shot. I know that I'm doing 80 shots, so I have a fixed number of trials. And I know that the success of his shots is the same throughout each trial of 61.3%. So this is definitely a binomial distribution with 80 trials and a probability of success of 0.613. Because remember, we always do this as N and P. So number of trials, proportion of successes, or probability of success. For B, it says, using the formulas, calculate the mean and standard deviation. So mu and sigma of X. So we know mu is N times P. That's going to be 80 times 0.613. And I'm going to do that off to the side here. Maybe. And I get 49.04. So the long-term average, if he makes 80 shots, we expect him to make about 49 of them on average. For standard deviation, or the spread about that mean, we're going to do the square root of N times P times 1 minus P, the failure rate. And I'm going to go ahead and do that on our fancy calculator. So square root, clear all that out. Square root 80 times 0.613 times 1 minus 0.613. And I get 4.36. Which is pretty small compared to a success average of 49 shots. So he's fairly consistent. Out of 80 shots, he's going to make about 49 of them, plus or minus about 4-ish. Next one says, use your calculator to find the probability that this player scored with 60 of these shots. And that's an exact value. So we made 80 shots. How many of them actually scored? So on our calculator, I know for equals, that's binom PDF. And in this case, we know N is 80. P is 0.613. And X is 60. And we're going to go ahead and plug that on our calculator. So we go second vars. We scroll down to binom PDF. N is 80. P is 0.613. And our number of successes is 60. And I get 0036. 0036. And I remember percent, I move the decimal place over twice. That's less than 1% chance that with a success rate of 61.3%, that he's going to make exactly 60 of his shots, which makes sense because his average is a little bit less than 50. Last one says, find the probability this player scored more than 50. More than 50. So x is more than is the same as greater than 50. And I know that's CDF because that's an inequality. We're going to scroll up and look for which function goes with greater than. And if I look, that's here. That's 1 minus binomial CDF. So on my calculator, I'm going to do 1 minus binomial CDF of P, or N, sorry, P and X. On our calculator, when we do this, we have to do the 1 minus before we do the second vars. Then we scroll down to CDF, 80.613, 50 in this case, and we get 37.18%, 0.3718, 3718. Or 37.18%. So given a success rate of 61.3%, there's a 37% chance that he's going to make more than 50 of his 80 shots. So getting exactly 60 shots is rare, but getting 50 or more is not that uncommon. All right, if you have any questions on binomial probability, feel free to send me an email. Otherwise, I will see you in our next video.